Good. Okay. So before we start, does anyone? Sorry, just let me share my desktop. Okay. Does anybody have any questions before we start? No. Okay. So we'll just what I'll do is I'll just go over the unit quickly. We'll have a look at the lab, and then we'll have a look at some sample questions from there. Okay, so we've covered our ciphers, fundamentals, symmetric key, hashing, and this week it was public key or asymmetric encryption. Uh, so you should find the details here of what you have to learn. I'll come back on to the public key challenge in a little minute. But just grab the presentation. So I'll very quickly go over this. So please, if anybody has any questions as I go along, if you could just ask from there. Okay, so there's fundamentally what we have with our public key encryption. There's that. So public key is used in three main places. So with public key, we use two keys, a key pair. We use one key to encrypt and only the other key can decrypt. We can use them either way around, and we typically define one as a public key that we can distribute to anyone, and the other one is a private key which we keep secret. So the three main methods is that we can obviously, if Bob wants to send a file, an encrypted file to Alice, she sends her public key. Bob then encrypts the data or the file with her public key, and she decrypts with a private key. So that works for small amounts of data, but it doesn't really scale to large amounts of data. So we would typically keep the amount of data to minimum because it gets difficult computationally to deal with large amounts of data. In normal operation, we use symmetric key encryption for this type of operation. The other method that we use it for is to be able to prove identity. So if Alice wants to prove identity to Bob, she encrypts some data. It could be a challenge, or it could be something that she has to sign, like a hash of a message, with her private key, and then she gives that to Bob, and then Bob decrypts that with her public key, and we should get the original data back. In this way, we prove our identity because only Alice can have the private key. And then the other method we can use, and we'll come on to key exchange next week, is that if Bob and Alice want to share a secret key or a session key, then Alice will send the public key to Bob. Bob generates a new key and then will encrypt that key with Alice's public key. He sends that back, and she then decrypts to find the session key, and they now have a shared key. So this method is used in TLS 1.2, and it's good for key exchange. The biggest problem with it is that if Alice's key gets hacked, then all of the keys that have been passed can now be cracked. So we have a problem. So in TLS 1.3, as we'll find out, this method has been dropped in exchange for a negotiated key exchange method that we'll cover next week. Does anybody have any questions about that? Good. So the three main public key methods that we have just now are integer factorization. We take two prime numbers and multiply them together, and it's quite difficult to be able to find the prime numbers which cause the multiplication. Discrete logarithms, where we take a generator value g and raise it to the power of secret x, and then take mod of a prime number, and it's difficult to find the original value of x. And increasingly we use elliptic curve methods. So that's used in smart cards, IoT, Tor, Bitcoin, and so on. The way that we typically measure the security of an encryption method is the amount of energy that we would consume to be able to crack a single key. So with 35-bit symmetric, we would need the energy to boil a teaspoon of water, and that's equivalent to 70 bits and 242 bits for public key. We can see that we can go up to around 80 bits, and we have range security, and anything above that needs a massive amount of energy to be able to crack our keys. So roughly we're about here in terms of the internet, about 72 bits symmetric key, 140 bits for our hash, and about 1,000 bits for our RSA. Anything below those values can be seen to be crackable within a reasonable cost. So RSA itself takes two prime numbers and multiplies them together, and it becomes an extremely difficult task to be able to factorize this back into the original prime numbers. A 1024-bit RSA modulus involves two 512-bit prime numbers, and there is a massive amounts of 512-bit prime numbers. The first method was proposed by Revest, Shamir, and Alderman, who created the RSA method in 1977, and it's still going around. Basically, we take two prime numbers, P and Q. We then determine the modulus, which is the two multiplied together. So this is a publicly available value and should always change every single time we create our keys. We then create phi, which is P minus 1 times Q minus 1. So in this case it's 20. And then we select a value of E, which does not share a factor with phi. So the factors of phi are 2, 4, 5, and so on. So we could pick 3 or 7. So let's pick 3. Our public key becomes 3, 33. So that's the N value and E value. We then must find a value for D. We'll multiply it by E and take the mod of phi is equal to 1. So we can use online tools. We can use Python to be able to find this. It's called the inverse mod function. But in this case, it's quite easy to see this one because 7 times 3 is 21. Mod 20 equals 1. So we found our decryption key as 7. So our decryption key is 7, 33. Does anybody have any questions about that part? Good. So we use an exponential cipher. So we take our message and we raise it to the power of E, take mod n. So that's, say, 5 to the power of 3. Mod 33 is 26. To decipher, we take the cipher, raise it to the power of D, take mod n, and hopefully we'll get the original value back again. So we've got some examples online and some little tutorial examples that you can go through, but to make sure it all works, go through a simple example, pick your message, and then it should all work out with the resulting value. If you pick the wrong numbers, say for D, you should not get unlikely to get the original value of the message back again. The other method and one of the most popular methods. So the problem with RSA is that we're now up to 4,000 bit RSA and on some sites, so it can become difficult, especially on a mobile phone or an IoT device, to run RSA. So RSA is kind of going, and elliptic curve is coming in its place. Elliptic curve looks a little bit like this. Well, it looks like that. This is the equation that we have: y squared is equal to x cubed plus ax plus b, and we pick a value of a and b to give us a certain type of curve. What we do is we pick a point on the curve, an xy point, and then for our private key we pick a gradient. The gradient is then plotted, and then the point at which we cut the curve again is now our public key. The difficulty here is that even though we know G, this point, and P, this point, it's almost impossible for us to be able to determine what the value of N actually is. Unfortunately, when quantum computers come along, then this method won't be that difficult, and it could be easily crackable. But it works just now, and it's very efficient for things like Bitcoin, IoT, and for Tor. They use this curve here, 25519. If you want to have a look at it, then it should be plotted here. Let me find where it is. This is this one here. Okay, that's what it looks like. And this is another common curve here. A equals 0 and b is equal to 7 there. Okay, so that's what our curve looks like. The other thing is that we bring in a mod of p. We have a prime number, and it doesn't end up as a curve, it ends up as discrete points that we map. So we see elliptic curve within Bitcoin, so we'll cover Bitcoin in more detail. But with Bitcoin, we take a private key, which is a random number, 256 bits. We then take a point G and multiply our G by this private key, and we end up with a 512-bit public key, which is an XY point here. From there, in Bitcoin, we can then derive what your Bitcoin address is from there. So the private key leads to the public key. This is an example of a transaction within Bitcoin. So Bob wants to send Alice some Bitcoins. He takes the transaction, finds out what Alice's public address is, adds it to the payment details, and then he will then sign the transaction with his private key. The public key can then be used to prove that Bob actually created the payment, and everyone can see it, especially Alice, and Alice will now have been credited with a number of Bitcoins. So we can use OpenSSL to be able to generate our key pair. So this is us creating a key pair here of this type, and we're creating our private key. So the private key has certain parameters, as we've seen, the prime number, the G point, and so on. And this is the private key in here. After this, we can then view our key pair. So in this case, there's our private key. That's a scalar value. And here's our public key. This is an XY point. The 04 identifies a certain type of mapping, but if you count these bytes, you'll find it should come to 512 bits. This is 256 bits. Because we have 256 bits, then we have 2 to the power of 56 different private keys, and that is a massive number. We're never going to have the same private key existing anywhere else in the whole world at any time. Okay, so that's our key there. And we can look at the parameters of our elliptic curve. So in this case, it's 0 and 7, as we saw. There's the generator that we use. That's the G point. There's the prime number we're going to be using, and that defines basically our elliptic curve parameters. So we use it in things like elliptic curve Diffie-Hellman. So in a Tor network, each node generates their own key, and we negotiate that key using an elliptic curve Diffie-Hellman method between Bob and the node. We generate the purple key between Bob and this node, the green key, and so on. When we encrypt the data, we'll take the red key, encrypt it first, then the green key, then the purple key. So as it goes through each node takes their encryption key off, and we end up like this. So it ends up like an onion, and we eventually have the unencrypted value here. But the core of this is elliptic curve Diffie-Hellman, which we'll cover next week. So there's an example. We'll cover that in more detail next week. The other basic method that we have is discrete logarithms, or with LGAML, we take a g point, raise it to the power of x mod n, and it's actually quite difficult to find the value of x from there. Finally, we can use this method within PGP, or pretty good privacy. And this is an email system that allows Bob to authenticate themselves to Alice, and then for Bob to send Alice an email that is encrypted. The way it works is that Bob takes a message, takes the hash of the message, and then encrypts that with his private key. So we end up with a signed hash. That then gets added to the message, and then Bob creates a new symmetric key, such as a 256-bit AES key. He now takes Alice's public key and he'll take that key and encrypt the message and the hash, signed hash. He then takes Alice's public key and encrypts the email session key. When it comes back, Alice will take this encrypted key, and with her private key, she can then decrypt to find the key that was used to encrypt the message and the hash. She'll then decrypt that with this session key, and she ends up, and she can read the message. Then she takes the encrypted hash and decrypts it. She'll take a hash of the message herself, and she compares the hash. If they compare, then she's proven that Bob did send the message and that the message hasn't actually changed. So I think I sent you my public key, and let me try and find where my VM is. Okay, so we use GPG typically for this here, and what we typically do is that we have a keyring. So the keyring holds our public key and our private key, and then we add on other people's public key onto our keyring, so that when we receive a message, we'll automatically use their public key and we don't have to request it. So in this case, there's the list of the keys that I have here. You can see I have this one there, and I add the key. If I can find it, I can add the key onto my keyring, and then I just use the -d with the encrypted message to be able to decrypt the message. And here it's here. Okay, and that's the basis of public key. Does anybody have any questions? Nope. Good. Okay, so what we'll do is we'll go to the lab now. Okay, so there's a little demonstration of the lab, or most of the lab, on that YouTube link. So this is what a public key looks like. It's in base 64, and then we have our header and our footer there. Message, if we can find it, also has a similar type of format. Okay, so you should be able to read this public key in and then view it with this page here. It should give you the user ID, the key encryption method, key size, and so on. This is stored in the ASCII armored message format. The advantage with that is that we can paste it into a text editor, into the body of an email, and so on. And we don't need any editors to be able to view it. So this is a useful library here, the crypto.public key, and with this you should be able to encrypt and decrypt with RSA. At the end of this lab, I've given the full code that allows you to encrypt and decrypt with your public and your private key. This will generate a key pair, and then we export it into a PEM format. The PEM format is the base64 format that looks a little bit like text. The other format is a DER. A DER format is a binary format, so that's not so good if we're sending an email with an encrypted message. So we typically use the PEM format for copying and pasting it, or using plain text. Okay, so with OpenSSL, we can create our key pair, and we can export, we can put protection on our keys. In this case, we encrypt the key, the private key, with a password. So you should always do that. Never store a private key without a password, and always use a strong password on the private key, because if your private key is stolen or compromised, you can be in big trouble. You've got to revoke keys, you've got to reset systems, you've got to tell your external parties any software that you've signed will now become untrusted, and so on. It is very messy. So make sure that you know where your keys are. You possibly have a copy of them in escrow sometimes, because if you use your private key, you might be locked out of your hard disk if it's encrypted, and so on. So increasingly we use our SSH keys for connecting to GitHub and to, say, the Amazon cloud. So they will authenticate you. So what we do is we generate a key pair, and it looks something like this for your SSH, OpenSSH keys. We then can upload this public key to GitHub, and then when we log into GitHub, then we should be able to authenticate with these key pairs. We can also use it in other places, such as when we connect to our cloud infrastructures. So our keys should be stored on our instance, hopefully within the .ssh folder. There. And these are just dummy keys that I've got. There's the public key. And there's my private key. Okay, so you don't give away your private key. This here identifies that this key is encrypted and has a password with it. And, okay, so when we're using GitHub or something like that, then we add our keys there. I don't know if I can show you that, if any of you have done it at all.
Well, I tried to do it, but so I added the key, and whenever I tried to connect from my VM, I couldn't connect, and I tried VSOC as well, and it didn't work for me with
Yeah,
SSH.
yeah,
I tried HTTP, but with HTTP it asks for the username and password.
Yeah. Yeah, there is a slight problem with that, and we'll have a look at that. But you should be able to connect with HTTPS. Did it not unload your files?
Yeah, it did.
It did. Did it?
So if I put the repository as private, it will ask for the username and password. But if it is public, it will download everything.
Yeah. So if you make it private just now and see if you can connect to it. So it should ask you for your username and password. That's right. Um, so we'll have a look at that. But yeah, so just try to settings. Uh, Here is your keys. So you can see these are my uh, Git keys, my public key, and I've also got my GPG keys that you can generate also, and these allow you to sign your code updates. So when I'm uploading, then they will be signed by me. This is just used for authentication, where the GPG keys are used to actually sign the code. So when you look at your Git repository, you'll see beside it that that code update has been signed by a certain person, so it gives it more cred, more trustworthiness. Okay, good. Right. Okay, just need to find out where the lab is again. Okay, so we can do the same for elliptic curve. We're using this elliptic curve here that we saw before, and hopefully you've all been able to export the keys and have a look at the prime number and so on. Uh, some of you have had problems with this code, I think. And just let me try to see if I can get that code to work on this machine. It's in my code. Unit 04. It looks like there's been an update on this code. So that's t01.python. Okay, that's elliptic curve. So we're encrypting Bob's public key and Bob decrypts with his private key. So let's see if that's going to work. And our messages test. Yeah, so it works, but I think some of you who set up your own environment didn't have the same version. So you can do a pip install with a certain version number of uh, that Python code. I'll check to see which version that we're using so that you can run it on your own machine. But I think it should run on the VSOC instance if you want to have a look at that one. Did anybody have problems with that code?
Yeah, thanks, Bill. It's Michael here. Yeah, I had those issues, so yeah, thanks for that. I'll try with another version as well.
Okay. Yep. So sorry about
Yeah,
that. Yep.
I I had the issue as well, and I tried on VSOC. It works fine. I tried to copy as well the same library from VSOC to my machine, and it didn't work, even though they have the same version of libraries.
Yeah. I've got a few different implementations of elliptic curve, so I'll try and find you a more standard one that will work. I think it's this line here, isn't it?
I
Where you,
think the from what I read, PyElliptic doesn't support the newer version of OpenSSL, so that might be the issue, and the developer just gave up on updating it.
right, okay. Yeah. So yeah, so it's probably to do with the version, yeah, the version number of OpenSSL. I don't think I've installed the most up-to-date version. I just got a kind of fairly stable one. So maybe you want to downgrade your OpenSSL to make it work. Uh, it is a major problem with this type of code that a developer can make an update and it can break all your code. They can put backdoors in code and so on, and you'll never see the versions actually changing. So often systems will fossilize the version because an update can actually break your infrastructure. Okay, so we'll have a look at that. This one plots this curve with some strange looking points with a certain prime number. Have a look at that, see if you can make some sense of it. And with this one, we're using elliptic curve to do a signing process here as we would with our email. I don't know if anybody managed to get this one to work. Did anyone try this one for RSA?
Yeah, I think it worked. Yeah.
Great. Well, we've got a little Python program here that should do that inverse mod, and it should always work. And there's a simple way to calculate it if you want. That's the inverse mod in there. And I asked you to send me your... Yep.
Sorry, for E2, I didn't really understand it a lot because I tried to do the calculation myself and I couldn't get to understand it.
So it's easy with some numbers. So d times e mod phi is equal to 1. So phi is 20 and e is 3. Then 7 times 3 is 21, mod 20 is equal to 1. So that is a solution. So we're trying to find a solution to this. And it's called an inverse mod. So we can either search for it to find the value of d when multiplied by e, and take the mod of phi. We want to get it to equal 1. So we could keep searching for that, but luckily there's a method that we can use. I'll just show you that method here that does that for us. So as I said, 7 mod 20. So this should come, what did I say? 3. So 3. I picked an E of 3 and 20. This should give us a result of 7. Because 3 times 7 mod 20 equals 1.
Okay.
Hey, Bill, so that means on an exam, we wouldn't have to do like the Euclidean algorithm. We could just use this. All right, cool.
Yeah. I might ask you to explain a little bit about it, why that, well, not why that works, but maybe a little question about what it's really doing under the hood, solving this. But I certainly, if it would be very simple numbers that we would use in this. Otherwise, you can use this type of calculator. This is my little Python code that does this. That's it. That's it there.
Sounds good.
And it uses the extended Euclidean algorithm to do it. And then we search it. Obviously, the numbers we deal with in real life are massive numbers, so it can take a few seconds to generate this d value. Okay, does everybody get that one? I'm not expecting you to all get that one straight away, but maybe before the exam you can go back over this and make sure you understand it. Okay, so that's that. If you're really smart, then you'll be able to solve my little puzzle here. So I've given you an E value. This is the typical value that we use for E. We don't use 3 anymore. We use this value. So all of RSA uses that as an E value. I've given you the N value here. And you should be able to go online and find a factorization program to be able to find the two original prime numbers. And then once you found them, you should be able to decipher that. So it's quite tough to do that, but maybe if you've got some time, you could do some cracking from there. With 60 bits prime numbers, it's fairly easy. With 128 bits, it's a lot more difficult, and you'll need a GPU to do it. So if we went right up to 1000 bits, then you just wouldn't have enough computational power to actually factorize it out again. I've also given you a private key and a public key here, and I've given you a message that was ciphered. So remember, you'll use Bob's private key to be able to decrypt this message here. So that uses the Python code that I've given at the end of the lab here. Okay, so if you just paste in your key and your encrypted message, this should be able to decrypt it for you. Okay, and then there's a few questions here. I've given some examples of RSA, and there's a few little demos that you can try out. And this is the type of exam question that you can expect, something like that. Okay, does anybody have any questions? No, good. Okay, does anybody have any questions about material from previous units at all? If you're still working on the previous lab and you're stuck, is there any additional material you would like me to demo or to add that would help you? Remember, our test is in week 9, Friday, week 9. I'll give you a study guide in the next week or so to give you a heads up, and I'll release the draft of the coursework so you can have a look at what you need to do. We'll have a little mini project in week 6, that you can build something in there.
So the mini project and the coursework, those are two separate things?
There's two separate things, yeah. So I'll release the coursework then for you to start to work on it. It's basically looking at how you can develop a trust infrastructure and encrypt documents, and then try to understand how you can secure that, possibly looking at some new methods of encryption as part of that. Okay, good. Well, I think we've covered all the content. So the next unit that we're going to go into is key exchange. So I'll try and update the material over the weekend to finalize that, and the lecture should go live over the weekend. You should find that each unit has the live class lecture and just an outline lecture. And there should be a demo. But if there's anything that you don't quite understand, then just ask, and I'll try and create a little demonstrator for it. Any other questions?
Yeah, Bill. Is the NetSim is actually accessible for all the students?
NetSim, is that the Cisco simulator, is it?
Yes, yes.
Should be fine. Have you given it a try? I've not used it for a long time, but if I try this one, let's give that a try. There we go. Enable config host name. It seems to be okay. It's working. I mean, it's not. It's no way as good as the kind of emulators that you get now, but certainly if you want to kind of practice on some Cisco commands, it should be okay. If you have a problem with it, then just tell me, and I'll get it fixed for you. But you can just use
Yeah, I was asking that question because if you look on the sub tab, sub,
sub where is it? Sub.
yeah, move, or you see, oh yeah. No, it's not exactly the same. There was a place where it was actually asked me to log in, and actually to purchase it, and I
Oh
didn't.
no, no,
Okay.
you don't want to do that. I'll
Okay.
send you
That's fine.
the login details. It's Napier
Okay.
for that. So that yeah, so you should be able to just log in with that account.
Okay then. Okay. Thank you.
Sorry about
Okay.
that. Okay. Anybody else with any burning questions at all? I'll release the details of the test hopefully in the next week or two, and you can start your studying. But with our main tests, I know that you've got other tests possibly for other modules coming up, so I do understand that you might be busy with other things. But the Slack space is all set up. If you have any questions at any time, just ask there, and I'll try and reply back. On Moodle, there's also a bulletin. There's boards that you can post to if you want. I think most of you have been using the Slack channel. Seems to be easier to set up, but I don't mind posting things onto Moodle if required. Any other pressing questions? Nope. Good. Okay. Well, best of luck with studies, and I'll be back with another presentation next week, next Tuesday, and we'll cover key exchange methods, and it should give you a more complete picture of cryptography. Okay. Right. Well, thanks very much, and hopefully I'll speak to you next week.
Thank you. Bye.
Bye. Have a nice one.